All right, then the last speaker for the morning before lunch is Dr. Nikola Maksimovic from Harvard University. He did his PhD at UC Berkeley with Professor James Anelitis, working on bulk crystal growth in strongly correlated materials, and now he's a postdoc in Professor Amir Yacobi's group, working on quantum sensing microscopy.
Yeah, thanks for the introduction. It's great to be here. So I'm a postdoc here at Harvard in Amir's group. We make use of the tools at the CNS fairly frequently, and I think I'm the only NV talk in this entire conference, so I'm going to try to kind of keep it roughly the first half of the talk at a fairly high level, just describe the technique, what NV is capable of, and things like that. And then in the second part of the talk, I'll kind of describe some of the new physics that we think we found in a 2D magnetic insulator using NV centers. So first, I want to thank the collaborators, at least on the physics part of the talk. I want to thank the entire Yacobi group because I'll be showing data from the whole group there. But this was really kind of a collaborative team effort between folks here at Harvard, at MIT, and then theory groups at ETH Zurich as well. I kind of wanted to motivate, this session and the development of new techniques in general. Sort of if you look back in time at the original kind of discovery of graphene and 2D materials, this was roughly, let's say the first era of 2D materials was kind of focused on simplicity. Make very clean graphene sheets, only electrons, one band, very simple band structure, no disorder, no interactions, anything like that. And so you could essentially learn all of the properties of the material just by attaching 4 leads to it and doing a gate voltage map. That would basically tell you everything that there is to know, more or less. Ever since maybe 2018 or so, the kind of push has been to introduce very strong interactions into these 2D materials, either through twisting them, through certain stacking orientations, kind of make flatter bands, more interactions, more complexity, and things like that. And what this means is, these kind of very, let's say, conventional measurement techniques are not going to cut it anymore. I mean, to some extent, a lot of this work that's been done since 2018 is on establishing the phenomenology of these very complex interacting phases and these kind of heterostructure devices. But ultimately, we sort of need new probes for investigating these things at a local level. Their symmetries, their interactions. And what that means is you kind of need to develop techniques to probe dynamics on the nanoscale in these materials. So I want to give kind of a broad overview of NV centers in diamond, what they are, what they're capable of doing, what they're capable of sensing, and kind of go through some work that's been done in our group on using these defects. So at the simplest level, these are basically atomic scale defects in the diamond lattice. What it is a nitrogen substitutional atom and a vacancy that's bonded to it. The nitrogen donates 1 electron. The vacancy, generally speaking, in the types of defects that we're interested in, is ionized, so it's holding an electron as well. So that's kind of 2 trapped electrons in the diamond lattice. Those aren't going anywhere. And because this is a spatially anti-symmetric system, it's a kind of spin triplet is the ground state. So if you look at the electronic structure of this defect within the diamond lattice, diamond has a pretty large band gap, and then this defect has a complicated set of level splittings within that diamond lattice band structure. Now these levels will move depending on the applied magnetic field, electric field, temperature, strain, and so on. So if you can measure every single one of these levels, you have a very sensitive detector of a variety of physical fields, basically. These are all, roughly speaking, either optically addressable or addressable through microwaves, depending on the size of the splitting between them. The most common sensing modality, probably the one that you are maybe familiar with, is using this to detect magnetic fields. The way that works is you essentially apply a laser that excites from the ground state to the excited state. This decays down and it emits red photons if you're in the 0 state. Or if it's in the plus or minus 1 state of this ground state triplet, it's optically dark. It has to kind of shuttle through this intermediate dark state and you get less red photons. So if I just constantly drive the system with a green laser and a microwave that cycles between these two transitions, I can detect kind of the level splitting between the ground state and the plus or minus 1 excited state of that triplet. That is directly proportional to the magnetic field. That's just the Zeeman splitting of these two. So ultimately, what every NV measurement that measures magnetic fields, or most of them, they boil down to measuring the position of this peak. What's really nice about these things is that they're really, truly, basically point sensors. So you can bring them very, very close to the sample, and you can look at kind of magnetic textures in the sample on nanometer length scales. Roughly speaking, between 1 and 1,000 nanometers is something that's physically accessible. That's kind of dictated by the distance of your sensor to the sample. So I'll show one example of how this has been used in our group. What they did is they took these diamond nanobeams that each had kind of implanted NV centers in them, and you could measure as a function of frequency sort of the nanoscale spin wave resonance of the magnetic insulator on which the NVs are lying. So this is kind of applying an external magnetic field and sweeping the drive frequency. You have these kind of standard optically detected magnetic resonance branches. That's what I showed on the first slide. And then in addition to that, you can kind of detect this magnetic resonance coming from the underlying substrate. That's this magnetic insulating film. So that's nice. The other nice property about the NVs is that once you put them in a certain state, they will remain in that state for some amount of time. So this is where kind of the quantum sensing applications of the NV come in. And I'm going to give my interpretation of why quantum sensing tends to give you a little bit higher sensitivity than classical sensing of the equivalent process. So what this boils down to, this magnetic resonance tracking, it's just tracking this peak. I need to figure out if it shifts around as a function of time, as a function of space, whatever. Now, from a classical level, if I measure where my signal is largest, where my optical contrast is largest, the sensitivity is 0, right? I need to measure somewhere on this slope where also my signal is roughly 1/2 of what it is at maximum. So it's a trade-off. I either get more signal or more sensitivity. You can, to some extent, overcome this limitation using the quantum properties of the NV. So what I can do is I can initialize the NV state into its ground state of the triplet, and it's going to retain that information for some amount of time. So what I can then do is apply a cycling transition that's a fixed duration, which will put it into a coherent superposition of its ground and +1 or -1 states. Then I'll just wait some time, and over that time, this kind of quantum state will acquire a phase which is just directly proportional to how much this peak moves around. Essentially, it's a linear proportional process, and I can, at the end of that, project it back and just read out how much phase it acquired. So to some extent, I can overcome this limitation. I can measure on resonance where the signal is highest, and also the shift, the phase that I measure is just linearly proportional to the shift. So I'm both maximizing the signal amplitude and the sensitivity at the same time. This is done just by breaking up my measurement kind of in the time domain. And as a consequence of this, I mean, NV centers have kind of achieved a pretty remarkable precision or sensitivity relative to other magnetic sensing techniques. This is a fairly old plot, so at this point, I think scanning squid is kind of approaching NV center, maybe even a little bit better, but you can really see kind of you're almost at the level where you can measure a single spin if you get close enough to it. The other nice thing about NV centers is that you can basically apply different sets of pulse sequences to access dynamics over different frequency ranges. So you're not just limited to, let's say, 100 kilohertz or DC. You can sort of come up with different measurement modalities to access magnetic fields up to, let's say, 10 gigahertz. I mean, that's really pushing it, but 0 to like a few gigahertz is very accessible using different kind of pulse sequences. And then finally, what I want to point out is that to some degree, you can achieve local resolution of magnetic fields using this technique. Two of the common form factors that are used are either embedding an ensemble of NV centers into a kind of diamond membrane or a substrate and then placing your sample on top of it. and using a scanning optical readout to address one specific patch of that ensemble. The other technique is to keep all of your readout, your readout apparatus fixed and to just scan it around relative to your sample. So in this case, you can kind of a single NV center implanted into the surface of a scanning probe and move that around. So shown here are kind of two examples. This is a scanning probe that's created in our lab that has a bunch of pillars, each with approximately 1 NV center per pillar. Here we have a substrate that's kind of an entire ensemble of NV centers that we can spatially resolve using a rastered laser beam. And using this, you can achieve kind of all kinds of neat images, basically. You can achieve insight into devices and samples that are otherwise maybe inaccessible. Shown here is one example. This is a Josephson junction. This is basically a superconducting wire that's broken by a non-superconducting bridge, in this case gold. And you have an NV center and a tip, and you can apply a very low frequency, relatively low frequency between 100 and 500 kilohertz current bias to this Josephson junction, and essentially lock in using your decoupling sequence applied to the NV center. You can lock into the magnetic field generated by that current. So shown here is a very nice image of the stray field generated by the current in a case where you have a vortex in the Josephson junction. In addition to that, you can look at kind of 2D materials. In this case, I'm looking at a 2D chromium chloride sample. This is a magnetic insulator. It's a layered antiferromagnetic insulator. And what we're looking at is basically magnetic noise, magnetic time correlations coming from the sample as a function of temperature and space. So you can sort of see how across the magnetic phase transitions of the material, there's kind of a proliferation of magnetic fluctuations, both in space and temperature. And so you can use this to study kind of critical dynamics of very small samples. So that's sort of a broad overview. Hopefully, you take something away from that, learn about NV centers a little bit. The question that I would like to approach in this talk is attempting to use kind of these tools that the NV Center provides in order to study strongly interacting states, in the solid state in 2D materials. And in particular, I'm going to focus on this actually rather old problem, which is related to the interactions between spin waves in a magnet, in this case, a magnetic insulator. So we'll go through a little bit of the introduction there and then kind of our main findings. So spin waves, of course, this is kind of the textbook undergrad, solid state level example of a excitation in a magnetic lattice. These are kind of transverse oscillations of the spin. They can propagate with a certain frequency and wavelength. And generally speaking, they'll obey some dispersion relation that looks like this. So as you go to shorter and shorter wavelengths, they become higher and higher frequency. Again, these are kind of transverse oscillations. Now you can think of these as kind of particles into some sense. They're waves, but they're also kind of quasi-particles in the solid state. And so you can have kind of a thermally populated gas of these spin waves, and they can interact with each other, right? They can scatter from each other. They can scatter from the medium that they're moving through, in this case, the lattice. And this is kind of a nonlinear process. It basically leads to a down conversion of spectral weight to very low frequencies that lie below this kind of single particle dispersion. These can be considered longitudinal fluctuations. So rather than the spin precessing like this, it's kind of a precession in this direction. And depending on the nature of these interactions, you can realize kind of different regimes. So two of the main ones are very strong spin wave interactions with the lattice. In that case, you kind of realize this diffusive kind of continuum of fluctuations. This is, if you would like to imagine, like a gas trapped in a porous medium. It kind of diffuses around. On the other hand, if there's very strong interactions between the spin waves themselves, if they collide with each other predominantly, it's more like a fluid, right? It's going to exhibit kind of a collective sound oscillation. This is kind of a propagating oscillation in the longitudinal component of the spin. So this is very relevant, kind of these different transport regimes, if you're trying to make a spintronic device, which is related to transport of basically magnetization. You're generally speaking not exciting single magnons and watching them transport through a material. You're exciting kind of a broad continuum and seeing how it, let's say, moves across whatever device you're trying to create. This regime kind of has been predicted for a while. It's to some extent more interesting than this diffusive regime because this is typically, what particles in the solid state do. What it requires is essentially very, very strong interactions between the spin waves in your material. And this can be realized in materials that have kind of a high degree of spin isotropy, very isotropic spin structure. So the spin can sort of point in any direction it wants. And what it boils down to is essentially you need to move into a temperature range where you have this thermally populated gas of spin waves, which are colliding predominantly with each other rather than the lattice of the material. So shown here are kind of three examples. Yttrium iron garnet is a great example where this sort of behavior has been predicted. Chromium chloride is a van der Waals magnetic insulator that is also extremely spin isotropic. And europium sulfide, this is a paper from like 1973 where this type of behavior was predicted at very, very low temperatures. So why hasn't it not been observed before? Why haven't people kind of looked for this behavior? Shown here is a conventional measurement technique. This is called inelastic neutron scattering, and this was done on chromium chloride, one of these candidates. You can see very well kind of the spin wave dispersion of this material in inelastic neutron scattering. Now, if you go to very low frequency and momentum, kind of the relevant range of these longitudinal fluctuations, in these measurements, you're limited by what's called the quasi-elastic continuum in neutron scattering. Basically, the neutron impinges on the material, it comes out without losing any energy, and it saturates the detector. So the bottom line is that many of the kind of classical measurement techniques of magnetic insulators do not have access to the appropriate length and time scales where you can sort of directly resolve these kind of longitudinal fluctuations. So we kind of wanted to approach this question using NV centers because we can access kind of this unique regime of time and length scales. So what we did is we took this kind of candidate material, chromium chloride, exfoliated it down using kind of standard Scotch tape methods in a glove box, encapsulated in HBN, and place it on the surface of a diamond containing an ensemble of NV centers in it. There's a coplanar microwave waveguide patterned directly on the surface of that diamond that's done using photolithography. So here's a schematic diagram of what it looks like. You have this set of NV centers that are buried roughly 55 nanometers below the surface, and you're therefore accessing kind of this length scale where maybe you could see signatures of kind of spin wave hydrodynamics in the material. So we can do some kind of basic characterization using these NV centers. This is the material that we're looking at, just to show you again the spin structure. It's kind of a hexagonal lattice with ferromagnetic exchange between the layers. In this case, we've isolated one single atomically thin sheet of this material. The stray field structure is kind of consistent with ferromagnetism in the sample, and from this you can extract the magnetization. And then we can look at the dynamics. So we can look at kind of the magnetic fluctuations emitted by presumably the spin wave gas in this material. So this is done using what's called the spin echo sensing protocol, where you can look at magnetic noise generated by the sample. And if we look at where the magnon, kind of these transverse spin oscillations are expected to lie in this material, we are measuring extremely far below kind of the frequency of those transverse oscillations. So this is a good indication that what we're probing here is kind of longitudinal fluctuations of the spins, i.e. kind of the interactions between the spin waves. So we think we've collected kind of two pretty good pieces of evidence for spin wave hydrodynamics in this material. The first is based on the kind of anomalous scaling of the fluctuations emitted by the material as detected by the NV center. And the second is kind of this more direct evidence for a hydrodynamic mode, a low-lying hydrodynamic mode in a multi-layer stack of chromium chloride. So let me go through the first piece of evidence here. Shown on the top here is a measurement of the magnetization of the sample, essentially the ferromagnetic moment of the sample as a function of temperature. So it's got a fairly low transition temperature, something like 12.5 Kelvin. But as you cool it down, the magnetization progressively freezes. Presumably, you're kind of freezing out the thermal fluctuations in the material. Now, on the other hand, we can measure kind of low-lying noise generated by the sample. This is sort of 25 to 100 kilohertz noise. And that actually also increases as you cool the sample down. So it's a little bit of a paradox in this sense. This can be very well understood theoretically by the fact that you are measuring emissions generated by this low-lying hydrodynamic longitudinal mode. Because this is a mode that's stabilized between interactions between the spin waves, as you increase the temperature, you increase the density of those spin waves and it becomes sharper and sharper. So if I'm measuring kind of fluctuations at this very low temperature, much of the spectral weight is getting kind of shunted to higher and higher frequencies. That's the interpretation. We've done kind of a more rigorous calculation and sort of modeling of this trend. And qualitatively, it seems to capture the general behavior. What you're measuring is kind of the viscous damping of this low-lying hydrodynamic mode, which kind of increases as temperature goes down. This is nice. It's a kind of a satisfying interpretation of the data, but we wanted to collect a little bit more direct evidence for this kind of low-frequency resonance. So what we did here is, for various reasons, we needed to boost the signal in this measurement. So we stacked basically a bunch of monolayer chromium chlorides. They have a weak antiferromagnetic exchange interaction between the layers. It's roughly 10 to 50 times lower than the ferromagnetic exchange between the layers. Generally speaking, the kind of consensus in the literature on this multi-layer stack is that predominantly the spin dynamics are kind of confined within the layers. There's a very slow process of spin movement between layers. At the static level, so the sort of magnetization of the material as a function of temperature, the way that this manifests is as two transitions. The first is a transition to a state where you have ferromagnetic order within the layers. And then if you cool down further, kind of you get an anti-alignment of the spins between the two layers. That's at the static kind of zero frequency limit. Now, what we sort of needed to do is access kind of the higher frequency response function of the material. The way this is done is kind of with this technique that was sort of developed a while ago in the quantum sensing community. The idea is to apply a high frequency, let's say a few hundred megahertz excitation. The sample will respond at that frequency, and then these can be mixed down by the NV center to something that you can detect with kind of a standard spin echo measurement. So shown on the right here, I'm sort of varying the bandwidth of this drive, and you can see a strong peak in the signal when the bandwidth of the drive intersects with my sensing frequency. That's kind of the way this can be interpreted as this down conversion process of the signal that the sample is generating. I'm not going to show this in this talk, but we've also done measurements where we kind of apply multiple tones, so multiple coherent tones, and look at kind of the mixing of those two frequencies down to lower. So you can characterize kind of how the signal generated by the sample varies with drive power. It's completely linear. And all of this is sort of consistent to some extent with kind of this down conversion process, which is a linear response of the sample at the frequency that you're applying. So what we can do is kind of apply a variable frequency stimulus and detect the down-converted signal on the chromium chloride multilayer and then on the bare diamond itself. So bare diamond doesn't show any response. You're just applying a single tone. The chromium chloride exhibits this down-converted signal, and in particular, what you see is this broad kind of peak feature centered at like 300 megahertz or so. Our interpretation is that this is kind of evidence for this hydrodynamic magnon sound mode, so this kind of propagating longitudinal excitation within the layers of the material. Theoretically, it's kind of maybe a factor of 2.5 off from the kind of first principles calculation that we've done. We think there might be some effective mass renormalization of the magnons or something like that. But what you can do is track kind of how this spectrum in the sample evolves as a function of temperature. This resonance frequency is basically totally unaffected by the transition to an interlayer antiferromagnetic state. It totally doesn't care about the interlayer arrangement of spins. We think that it's kind of confined to the ferromagnetic layers. If you're interested, this kind of Lorentzian tail appears to exhibit kind of a sharp inflection point at that transition. So there may be kind of a very slow interlayer spin hopping process that kind of exhibits a critical slowing down at that transition. But for the most part, we kind of focused it on the behavior of this resonance. And one of the kind of notable features is that the damping rate seems to increase as temperature goes down. So it gets broader and broader as you cool the sample down. And this is kind of consistent with our original interpretation of the noise measurements of the monolayer, where you kind of have a damping rate set by the viscosity of the spin waves in the material. So yeah, I'm kind of approaching the end of my talk, but one of the things I wanted to point out is that this type of behavior, this kind of hydrodynamic modes or longitudinal modes in magnets, was predicted a very, very long time ago. 1969 or 1968 is when people kind of first came up with the idea, and it's taken a very long time. And I think it's required kind of advances in sensing techniques to access the appropriate kind of time and length scales relevant to this process. So yeah, I want to kind of wrap up my talk and sort of just give a broad kind of general future direction for this technique. I'd say the field is kind of divided somewhat into two: these people who do kind of hardcore quantum sensing development, and then these people who sort of make these very complicated materials with very strong interactions. And where we would like to sit is kind of at the interface of the two, is to apply these new techniques to these new materials and see kind of how they can feed back into each other, what you can learn from this interface. So yeah, that's the end of my talk. Thanks.
All right, thank you very much. And for those of us on the periphery of this community, it is really impressive how sophisticated this work has gotten over the years. It's pretty awesome.
Thanks.
Do we have a few questions before lunchtime?
Thanks. Do you see edge effects? So if you have a flake, if you probe it in the bulk versus the edge, right? If this is hydrodynamic, you should start to see effects of viscosity.
Yeah, we do. It's not something that we completely understand at the moment, but there is kind of different behavior at the edge and the bulk. Yeah. We can talk more after if you're interested, yeah.
More basic question. How do you create those NV centers?
So we, generally speaking, I mean, we generally outsource them, the creation of these. So you can kind of implant, you can send them out to a company that implants, do some annealing, and then you need to ionize them somehow. Generally speaking, you can do some sort of like electron irradiation or something like that. But yeah, we sort of outsource that process for the most part, other than the annealing. Yeah.
All right, I think I saw one more over here somewhere. No? Okay, in that case, let's thank our speaker one more time.